Hi, welcome to this video about removal of natural organic matter, or NOM, with ion exchange and coagulation. My name is Klaas Schoutteten. I am a postdoctoral researcher. Together with the Watergroep, a drinking water utility in Belgium, I am working on the DOC2Cs project. In this video, I will briefly explain how ion exchange and coagulation work. After this, I will show you the results from two cases at the Watergroep where these two technologies have been combined for removing NOM from water. First, what is ion exchange? You probably already use this technology in your home, for example, in your water softener, in your dishwasher, in your water filter, or perhaps you even use one of these special shower head softeners. The common goal of these appliances is to remove hardness from water, so the calcium and magnesium ions are removed. The material used for this is called an ion exchange resin. If you would look inside your dishwasher, or if you would cut open your water filter, you would see that they indeed contain ion exchange resins. There are four major types of ion exchange resins. Two of them are cation exchange resins and two of them are anion exchange resins. Cation exchange resins can be used for water softening, while anion exchange resins can be used for removing NOM from water. I will only briefly touch the mechanism of ion exchange here, but if you would like to know more, please watch the video of Erik Koreman on NOM removal by ion exchange. In short, the ions on the resin are exchanged for different ions present in the feedwater, having a higher affinity for the resin. And the affinity is a function of the charge density of the ion and its concentration in the feedwater. For the surface water at the Watergroep, the affinity of the most important ions is shown in the following series. So, if we have a resin in chloride form, then sulfate and NOM from the feed water will bind to the resin, while chloride will be released. After a certain runtime, the resin will be saturated and the removal of the target ions will decrease. At this point, the resin is regenerated with a concentrated solution of a low affinity ion. In our case, this is a solution of sodium chloride called the brine. During regeneration, the resin is put back into chloride form, and the previously bound ions will end up in a stream called the spent brine. There are different types of ion exchange reactors, and the first type is a fixed bed reactor. This type of reactor is often used for water softening, but it cannot be used when suspended solids are present in the feedwater, because then the particles would clog the fixed bed reactor. Another reactor type is a suspended bed reactor, where the resin is mixed with the feedwater and externally separated from the water. Yet another system is a fluidized bed reactor, where the resin is gently fluidized inside the reactor. However, it stays in the reactor because only a low upwards velocity is applied. In this case, regeneration can occur inside the reactor or through periodically withdrawing a small part of the resin from the fluidized reactor and after regeneration dropping it back inside the reactor. Both systems can accept feedwaters containing suspended solids, and the fluidized bed system is the one which has been adopted by the Watergroep. The second technology we use for DOC removal is coagulation. If you would like to know more about the mechanisms of coagulation, please watch the video of Bas Heijman on NOM removal by coagulation. As Bas explains in his video, the impurities will aggregate into flocks which will need to be separated from the water. A first method to remove the flocks is by allowing them to sediment. This can be done in, for example, a decanter, where the water is in an upflow direction, and because of the shape of the decanter, the velocity of the water is decreasing. This allows for the heavier flocks to be separated from the water. Another method to remove the flocks is through flotation, where microscopic bubbles of air are introduced into the reactor, and they will attach to the flocks. The flocks will float towards the top, while the clean water exits at the bottom. As mentioned before, the Watergroep is investigating both ion exchange and coagulation for removal of NOM. In the current full-scale drinking water treatment plants, NOM is removed mainly through coagulation, and the research which is currently under investigation is a combination of ion exchange and coagulation, where the aim is to reduce the chemicals dosed during coagulation and at the same time improve the overall NOM removal. This concept is under investigation on pilot scale in in 2 drinking water treatment works of the Watergroep, in Kluizen and in de Blankaart. A very important site-specific consideration is that no liquid waste streams can be discharged at either location. And this means that the spent brine must be treated on-site. And this is done by coagulating the organics. After this, sodium chloride is added and the solution is then reused as brine for a next resin regeneration. This means that during regeneration, for every bed volume of brine, only a maximum of 1 bed volume of spent brine can be collected. And this implies that after resin regeneration, the resin cannot be rinsed to remove remaining salt. Thus, there will inevitably be some chloride loss into the drinking water. This brings us to the following table. If the resin would be regenerated frequently, a high NOM removal will be observed. However, at the same time, the chloride loss will also be high, and vice versa for infrequent regeneration. Looking at the pilot plant results of Kleusen, we found that implementation of ion exchange before coagulation improved the removal of NOM, and at the same time significantly decreased the required coagulant dose. And these are very good results. However, at the Blanckaert, we found no improved NOM removal, and the coagulant dose could only be decreased slightly. So then, why does a combination of a fluidized bed ion exchange and coagulation work at Kleusen but not at the Blanckaert? A first reason is a difference in the way that the standalone coagulation is being performed. In Kleusen, coagulation must be done with polyaluminium chloride at a pH of 7.3 because of flock strength requirements. While in the Blanckaert, the coagulation is performed with ferric iron at a much lower pH. This means that less organics are removed in the standalone coagulation Kleusen, and thus it's easier to achieve a higher NOM removal by introducing ion exchange. Another difference is the sulfate and chloride concentrations in the feed water. Both are higher in the Blanckaert. A high sulfate content means that frequent regeneration is required if one wants to achieve a high NOM removal. However, because of the also high chloride concentration, frequent regeneration is difficult since too much chloride would end up in the drinking water. Concluding this presentation, applying ion exchange before coagulation to reduce the coagulant dose can be a great success. However, limitations occur when the spent brine cannot be discharged, when the feed water is high in sulfate and chloride, and when NOM removal is already high in standalone coagulation. Thank you for your attention.